Good morning. Today we will discuss the distribution of the arrival epochs Sn and the number of arrivals until time t n of t of a Poisson process. So, recall that we defined a Poisson process as a counting process where these interarrival times x1, x2 etc. are IID exponentials, right. So, if this is if and these are of course the arrival epochs S1 S2 dot Sn, right. We know that Sn is equal to sum over xi from I is equal to 1 through n, right. So, the distributions of xi's are independent identically distributed exponentials with parameter lambda. So, what is the distribution of Sn? Multiply in Laplace domain. Of course, see, the basic thing is that these are independent random variables. So, you can the density of the sum is given by the convolution of the density of each of these, and of course, the density of each of these is the same, which is an exponential, right. So, if you take fx for each of these xi's, fx is just lambda e to the minus lambda x for x bigger than or equal to 0, right. And since these xi's are independent, we can write, since xi are IID, we can write fSn is equal to fx convolution fx convolution dot dot dot, it is an n-fold convolution, right. This is a n-fold. So, you can sit and convolve the exponential distribution n times, or if you know something about Laplace transforms, you can take Laplace transform, multiply it, right. So, you take the nth power of the exponential's Laplace transform and then invert back. So, what you get when you do this is something known as the Erlang density. Okay. So, you get fSn when you do all this n-fold convolution, you get fSn is n minus 1 factorial in the denominator, let me get this right, lambda to the n t to the n minus 1 e power minus lambda t for t greater than or equal to 0. All right. So, you can easily calculate the density of the nth arrival epoch. All right. Any questions? So, you put n equal to 1, you get back the, so for n equal to 1 what happens? S1, right, S1 is just x1. So, you should get back what? This is the usual exponential which you do, right. You can just put n equal to 1 and check that it works out. Okay. Now, this is just the marginal distribution of Sn, right. So, in order to specify the process, see what specifies a process is the joint distribution of these xi's or si's, right. The joint distribution of xi's, of course, we know they are all independent exponentials, but the joint distribution of si's we have to calculate, right. So, what we have calculated through this convolution formula is only the marginal. So, if I ask you what is the joint distribution of S1 S2 S2 Sn for any n, right, then what happens? It is a little more non trivial, right. See what I mean? So, question, what is the joint distribution of S1 S2 dot. Okay, this is the question. Now, let us do this for n equal to 2. Okay. So, S1 and S2 are the first two arrival epochs, right. Now, S1 and S2 are of course dependent, right, X1 and X2 are independent, but S1 and S2 are dependent, right. So, they have some joint distribution, okay, which is not just the product or anything, right. Now, of course, S2 has to be bigger than or equal to S1, so they are clearly dependent. So, what is F big S1 big S2 of little s1 little s2? You can write this as using the definition of conditional densities, you can write this as Fs1 of S1 times F yeah, this you know, right, you know the definition of conditional density, right. So, that is what I am using. The reason I am doing this is because once I condition on S1, right, the further time to S2 is well known. What is it? It is an exponential, right. So, I know that, right. So, I want to exploit that property, okay. So, you are looking at something like this, right. So, this is 0, that is S1, that is S2, right. So, given that this guy is realized as little s1, I want what is the distribution of that, right. So, given S1 is little s1, this width is just a exponential, right. So, if you want this to be little s2, then this width should be just correct, that is what we are going to use, it is very simple, right. So, this is of course, S1 is just x1, right. So, this is what the first term is lambda e to the minus lambda S1, right. So, you are conditioning now on S1 and you want S2 to be little s2, right, which means that the realization of x2 should be S2 minus S1, right. So, that you can, right, this is just the probability, this is just the density of the x2 evaluated at S2 minus S1, correct, and this is true for all S2 bigger than or equal to S1 bigger than or equal to 0, correct. Any questions? I am just using the fact that condition on S1 S2 minus S1 is an exponential, S2 minus x1 is S1 is x2, right, that is all that I am using, clear. So, what does that work out to be? That works out to be lambda squared e to the minus lambda S2, right, because this cancels with minus lambda S1, correct, yes, and this is true for S2 bigger than or equal to S1 bigger than or equal to 0, all right. So, the joint density of S1 and S2 is lambda square e to the minus lambda S2. Now, where is S1? See, this f of S1 S2 should be a function of S1 and S2, right, but it is only a function of S2, which means it is independent, yeah, it is constant, it is constant in S1, except that I mean the S1 shows up in the constraint, correct. So, S1 has to be less than or equal to S2, it clearly has to be, right. So, the if you look at the 2 dimensional plane, let us say this is S2, that is S1, the density is non-zero only in the range S2 bigger than S1 greater than 0, right, bigger than or equal to 0. So, it is non-zero only here, correct with me, is that clear to everyone? And as a function of S2 there is a dependence e to the minus lambda S2, but as a function of S1 which is I have drawn in the vertical axis, it is constant. So, if you pick any S2 and you change S1, the density remains constant, right, the density is coming out of the plane of the board if you like, right, yeah. So, it is decaying in S2, but constant in S1 and it is defined in this region which is below the 45-degree line. Now, you can do the same trick for S1 through Sn, okay. So, we can state this now proposition. Once you understand the case n equal to true, the case for general n is easy. The joint density of S1 S2 dot 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 Sn is given by f S1 S2 Sn of little s1 little s2 little sn is equal to lambda to the n e to the minus Sn for Sn bigger than or equal to Sn minus 1 bigger than or equal to dot dot dot, correct. I missed out the lambda, let me write this, sorry, that is correct. So, again this joint density of S1 through Sn is explicitly a function only of Sn, correct, but the other random variables S1 through Sn minus 1 occur in the constraints. So, in an n dimensional space, of course, all of these are non-negative random variables. So, you could anyway looking at only the non-negative orthant, right, and in the non-negative orthant it exists only in a part of the orthant where the nth coordinate is bigger than the n minus 1 coordinate is bigger than the n minus 2th coordinate and so on, all right. Similar to the picture I drew here, this picture right here, except in n dimensions, okay. So, this is the joint density, okay. How do you prove this? Yes, proof is by induction. In particular, for the case n equal to 2 is you already proved, right, you make n equal to 2 the base case, right, you already proved from first principles. Then you make an induction hypothesis saying that the kth joint density is this, right, then you look of S1 through Sk, then you look at the joint density of S1 through Sk plus 1, okay. Then you write that in terms of the joint density of the first k times the conditional density of Sk plus 1 given all the previous guys. Of course, you have an induction hypothesis for the first term which is the joint density of the first k, and then of course, the conditional density given the first k is simply another exponential, correct. Then you will the same trick works, okay. Induction will do the job, okay. I think you can complete this easily, all right. The distribution of n of t. So, we are fixing some t, okay. N of t of course is a random variable, right. You fix t equal to 10, t equal to 100, whatever you want, and you are looking at the total number of arrivals until the time t is of course a random variable, and you are looking at its distribution. It is a non-negative integer valued random variable. So, you are talking about the, so for non-negative random variable integer valued random variable you have to talk about the PMF, right. So, you want to get the probability mass function of n of t. So, you want the, so you want this, want probability that NT equal to n, all right. So, we can denote this by P NT of n, okay, is a PMF, okay, probability mass function of n of t for some t greater than 0, for a fixed t greater than 0, okay. Now, you know, recall that there is this equivalence, right. Recall that the event NT is greater than or equal to n is equal to the event that, right, correct. So, from this you can essentially see, we know the distribution of Sn Erlang, right. So, probability that Sn is less than or equal to t we can easily write out, simply the integral of the Erlang density. This is nothing but the Erlang CDF, right, if you take probability of this, right. So, you can look at the probability of NT greater than or equal to n is easy to get, that is really all there is to it. Since you know the distribution of Sn, you can calculate the distribution of NT using this equivalence, okay. It is a mostly mechanical exercise, but you can do the following, for example. So, you can write, perhaps you can, this is well one way to do it, probability that NT is equal to n is what you want, right. P NT of n is equal to P NT sorry, P NT is this correct? Maybe not, no, this is not correct. So, I want to write greater than or equal to n. If I write n minus 1 here, I will be okay, right. So, maybe I should write it like this, sorry, I am off by 1, right. I think you will agree if I write yeah, anything wrong here? No, I changed, I mean I was off by 1, now I think I am okay, right, this is correct, yeah. So, but now this is of course equal to probability that minus probability that correct. Why? This is from the equivalence, correct. So, this you can write as integral 0 to t lambda to the n. Now, I have to look at the Erlang density again, right. I do not remember it off the top of my head. So, Fsn of t is nothing but lambda to the n t, I should not write t again. So, I should write perhaps I will write tau, okay, tau to the n minus 1 e to the minus lambda tau over n minus 1 factorial d tau minus integral 0 to t, the same thing replaced with n plus 1 tau to the n e to the minus lambda tau over n factorial d tau, correct. What have I done? So, I want to look at probability Sn less than or equal to t, which is the CDF of Sn, which is the running integral from 0 to t of the Erlang density. See, I am writing tau here because I want the variable of integration to be different from what the limit is, right, that is why I have put tau if you are wondering why. And similarly I have done the same thing with n replaced with n minus 1. So, now you can fight it out, okay, there is nothing more to it, you do this integration by parts, whatever you have, you people do this faster than I can do, right. So, you finally you fight it out and you will get a nice answer, you will get this is equal to this answer I know, okay, lambda 2 to the n e to the minus lambda t by n factorial for n is equal to 0, 1, 2 dot dot dot. Of course, 0 factorial is taken as 1. Actually, see, you have to, you will directly get this for n is equal to 1 onwards, n equal to 0 you have to do it separately, because this formula will not hold, right, because you will get minus 1 factorial and all that does not make sense. For n is equal to 0, probability that n t is equal to 0 is nothing but the probability that x 1 is bigger than t, that we already know. N t equal to 0 is the same as the event x 1 bigger than t, right. Probability x 1 bigger than t is e raised to minus lambda t, right. So, nevertheless you get that for n t equal to 0, for n t equal to 1 onwards this calculation is valid, right. So, this calculation here is valid for n t 1 to 1 onwards, for n t equal to 0 you have to do it separately like I just spoke out, okay. But nevertheless the formula here will be valid, okay, if you take 0 n is equal to 0 factorial you will get it, okay. So, this is worth putting in a box, right. P n t of little n is equal to n factorial e to the minus lambda t to the n over n factorial, okay. This is called the Poisson PMF, okay. This is true for so n is equal to 0, 1, 2 etcetera. This is called the Poisson PMF. It is Poisson PMF with parameter lambda t. So, for any t, n of t is Poisson distributed with parameter lambda t, okay. Is that clear? Any questions? So, we know that what we did is we know Sn is Erlang distributed. So, using the equivalence between Sn and Nt, which we already derived, we just got it, okay, we just did some algebraic manipulations and got it, okay. So, nothing very greatly involved here, okay, except some big integrals involved, okay. Of course, the PMF of Nt alone is not satisfactory, right. What do you actually want? You want the, see, this Nt is a sequence of random variables indexed by t. So, you want to characterize all finite order joint distributions of n of t 1, n of t 2 etcetera, correct, just like S 1 through Sn, right. Here for any given t 1, t 2, t k, you want the joint PMF of n of t 1, n of t 2, n of t k, correct. So, that is the next thing we will do. Yes.
Actually, you can directly integrate, right, because the variable of integration is tau. So, you will never get a minus 1 factorial.
Sorry, so in this
you can directly integrate it.
No, I mean see this whatever I have written down here, right, this expression out here is valid for n bigger than or equal to 1, correct. So, all of this is true for this guy is true for n bigger than or equal to 1, right. So, I should really write, so I can only write n is equal to 1 2, right, because this expression is valid only for n bigger than or equal to 1. I am sneaking a 0 in by saying that you can make a separate argument for n t equal to 0, that is all, okay. All right. Okay. Now, joint distribution, joint PMF fix. So, fix some k greater than 0 and 0 less than T 1 less than T 2 dot 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 less than T k. Okay. So, you want to join PMF of n of T 1, n of T 2 etcetera, right. So, what is probability that n of T 1 equal to n 1, n of dot 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 okay. Now, again it is easy to do I mean you will take any this k is equal to 2, right. So, what is the joint PMF of n of T 1 equal to n 1, n of T 2 equal to n 2, right. So, you first take k equal to 2 which is the simplest case, right. We want probability that n of T 1 is equal to n 1 and n of T 2 is equal to n 2. Okay. This can be written as probability that n of T 1 is equal to n 1 times the probability that n of T 2 equal to n 2, yeah. So, let me write this here, okay, times so probability that n of T 2 equal to n 2 given, yeah, this is by this conditioning, right, got it. So, which just comes down to see probability n t equal to n 1 I already know, n t 1 equal to n 1 I already know, right, that is equal to lambda T 1 to the n 1 e to the minus lambda T 1 over n 1 factorial, that is just the first term which I already know. Then you are looking at given that n of T 1 is equal to n 1, what is the probability that n of T 2 equal to n 2, correct. Now, you have to use some property of the Poisson process, right. So, if there are, so there have been n 1 arrivals till T 1, you want another n 2 minus n 1 arrivals to come in an interval of width T 2 minus T 1. See, by the stationary increment property, the number of arrivals in any interval is only a function of this bit which is T 2 minus T 1 in this case, right. Also, given that there are n 1 arrivals till time T 1, the number of arrivals in T 1 to T 2 is independent of number of arrivals in 0 to T 1. Why? Independent IIP, independent increments property. So, you have to use both SIP and IIP to calculate this guy, right. So, this requires so let me write this lambda T 2 minus T 1 e to the minus lambda, sorry, whole to the n, I forgot a term here, right, whole raised to n 2 minus n 1, you want n 2 minus n 1 arrivals in the interval T 2 minus T 1 times e to the minus lambda T 2 minus T 1 over n 2 minus n 1 factorial, right. This is of course true for n 2 bigger than or equal to n 1 bigger than or equal to 0, right, correct. And this for this particular term, to get this term I have used SIP and IIP, right. So, to just give you a picture, this is 0, this is T1, that is T2. So, you had some N1 arrivals here, right. So, given that you had N1 arrivals in 0 to T1, you want to have another further N2 minus N1 arrivals here, correct. Of course, by the stationary increment property, the number of arrivals in T1 to T2 has the same distribution as the number of arrivals in 0 to T2 minus T1. And what is more, given that there are N1 arrivals in 0 to T1, the number of arrivals in T1 to T2 is independent of this number of arrivals have already taken place, right. So, I am using both these things together to write this, right, clear. Is that clear? So, now I can, so similarly for k I can write down, right, same trick works. I hope I do not make any mistakes, let me write this down, okay. N of T1 equal to N1, N of dot 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 N of Tk equal to Nk, right. This will turn out to be equal to lambda T1 to the N1 e to the minus lambda T1 by N1 factorial times lambda times T n sorry T I minus T I minus 1 whole raised to N I minus N I minus 1. Say I may be off by 1, let me see if this is correct. There should be a pi here, right. Product I is equal to 2 to k, I think. Let me verify this. T I minus T I minus 1 whole divided by N I minus N I minus 1 factorial. Is that correct? Because condition, you can do this repeated conditioning, you can, in particular you can use induction, you can use the previous result as a base case, make this induction hypothesis for k and prove it for k plus 1, okay. This expression is basically you do this multiple times, whatever I did before for 2 you do this multiple times, okay, and I hope there are no off by 1 errors here, looks correct, right. All right. So, that is the joint distribution of these. So, any given any k and T1, T2, Tk, you can calculate the joint distribution of n of T1 through n of Tk using IIP and SIP, okay.